All right, this video is to introduce the formula for what is called the decibel scale. And it's nothing more than a measurement similar to the Richter scale, but it's for the intensity of sound. So as it reads here, the psychological sensation of loudness varies with the logarithm of the intensity, and that is the Weber-Fechner law. And so the intensity level measured in decibels, or dB, is defined as, and here we use the Greek letter beta to represent the decibel level of the sound. It's going to be equal to 10 times the common logarithm of the intensity of this sound as compared to the what we call the reference intensity. And this actually should read, let's see here, it looks like there's a little bit of a typo in this slide, but this should read I-O, I sub O, and this here should be 10 to the negative 12. I believe I've corrected it on the handout, but it's just not for this video. All right, 10 raised to the negative 12th watts per meter squared at a frequency of 1,000 hertz, which measures a sound that is just barely audible, and that is, we call it the threshold of hearing. And so in this case, we call it a decibel because it's being multiplied by 10. That's our what DESA stands for, and the Bell comes from the fact that this scale was invented at Bell Laboratories. All right, so let's take a look at how we would use this. It's going to be very similar to a problem that involves the earthquakes or the Richter scale. So let's take a look at an example. The intensity level of a normal conversation is 60 dB, or 60 decibels, while the intensity level of a normal whisper is only 30 decibels. How many times more intense is a normal conversation than a whisper? So like I did for the Richter scale problem, if you've watched that video, I need basically is to create two equations. I'm going to determine their intensities, and then I'm going to compare the intensities. So here we're going to say, this first one, we'll call it the normal conversation. So this would be the equation for the normal conversation. And over here we'll have for the normal whisper. So that'll be for the normal whisper. So we were told for the normal conversation that its decibel rating was 60 dB. And that's going to be equal to 10 times the common log of the intensity of that conversation in watts per meter squared divided by 10 raised to the negative 12 power. Okay. And then for the whisper, we're going to have something very similar. I'm going to have 30 dB. And actually, I don't need to write decibels in here because that's not part of the equation. Let me just get rid of those. And again, it's going to be equal to 10 times the common log of the intensity of that whisper in watts per meter squared. And so we measure sound with what's called a power meter. Right. Or that's one device. You've probably seen them on, I don't know, you might have seen a TV show. They used them a lot, like on Mythbusters. I've seen them used in other television shows where they're measuring like the noise in a stadium or something like that. Let's see. So both of them are multiplied by a power of 10. So before I can rewrite them in exponential form, I need to get rid of that. So I'm going to come in and I'm going to divide both sides by 10. Okay. I'm going to divide both sides of both equations by 10. This is doing nothing to the logarithm. This is just getting rid of the 10 in front of the logarithm, right? That's all it's doing. So over here on the left for the normal conversation, this will give us that 6. And that would still technically be in, well, I don't know if it's in decibels anymore, so I'm not going to say that it is. But we'll have 6 is equal to the common log of the intensity divided by that 10 to the negative 12 threshold of hearing in watts per meter squared. And for the whisper, we'll have a similar thing. We'll have 3 is equal to the common log of the intensity divided by that 10 to the negative 12 watts per meter squared. 12, there we go. for that threshold of hearing. There we are. All right, now that I've isolated the logarithm on those right-hand sides, now I can go ahead and rewrite them in exponential form. So since they're common logarithms, this one on the left for the normal conversation is going to be 10 to the 6th power is equal to the intensity of the sound divided by 10 to the negative 12. All right, 10 to the negative 12. And over here for the normal whisper, we're going to have 10 raised to the 3rd power is equal to the intensity divided by 10 to the negative 12. So as you can see, they're both divided by 10 to the negative 12. So that means I'm going to need to come in here and multiply both sides of both the equations by 10 raised to the negative 12. And when we do that, again, just like in the Richter scale problem, I mentioned the property of exponents that said when we multiply two factors that have the same base, we're going to add the exponent. So this is going to give us 10 raised to the negative 6th power is equal to the intensity for this normal whisper. And over here on the right, same thing. I'm going to multiply by 10 to the negative 12 power. All right. And I forgot to mention over here on the left, that's all that's doing is simplifying out the 10 to the negative 12 where the intensity was divided by it. So over here, it's doing the same thing. Those are simplifying out. And again, I'm multiplying two factors with the same base, so I'm going to add the exponents. And so here for the normal whisper, I'm going to get 10 raised to the negative 9th power for that intensity. Now, we could go ahead and use a calculator to evaluate these, but anytime it's to a nice integer value, I know really this is just going to be a 0 with one less 0 behind the decimal and then a 1. So that means I'm going to have 5 zeros here and 1. That's the intensity in watts per meter squared for the normal conversation. It should be a capital W. There we go. And then for the 10 to the negative 9, that means I need to have 8 zeros behind the decimal, because the 1 counts as one of the negative values. So there's our value for the normal whisper, and again, watts per meter squared. Now remember, the problem didn't ask us to find the two separate intensities. It asked how many more times intense is that normal conversation. So similar to the Richter scale problem, we're going to do something similar. So we're going to come back here. We're going to come to our calculator. And so now what I need to do is take the larger of the two intensities, which, believe it or not, is the 10 to the negative 6th power. So I'm going to say 0 point, and I need 5 zeros. So 1, 2, 3, 4, 5, and then a 1 divided by, I'm going to say point, so I forgot the 0 in there. 0 point, I think you can do it without it, but that's fine. 1, 2, 3, 4, 5, 6, 7, 8. I just wanted to make sure I had the right number of zeros in there. I believe I do. So 2, 4, 6, 8. Yep. And so it turns out that this normal conversation, the sound from it, would be 1,000 times more intense than it is for normal whisper. All right, so that's what we have here. So we're going to have the intensity of the conversation divided by the intensity of the whisper. That's all we're doing. We're taking those two intensities like you just saw me do on the calculator. I'm dividing the two, and we come up with that it's about 1,000 times as intense. That's not to say that a normal conversation is going to rupture your eardrum by any means, all right? It's just more intense than that of a normal whisper. So to put this in perspective, I think I want to say, like, if you were standing somewhere close to, like, say, Raleigh Durham Airport, and a jet airliner was taking off, and I can't remember the distance. I want to say it's like 100 yards from the flight line. The jet airliner, I think, at its loudest point is like 130 decibels. So it's over twice the noise of a normal conversation. And that's it for the decibel scale.